Hello everybody and welcome to exercise 8. And this is an exercise on finding the interval of convergence of power series. In this video we're just going to look at the power series that you see in part A. Now remember the idea of a power series. When they say find the interval of convergence, they're asking us to determine the values of x for which this is a convergent series. This series has a variable in it, and so it's going to converge for some x's and maybe diverge for other x's. We'd like to know what the x's are for which it converges. Okay, and the nice thing about a problem like this is that we always start out in the same way using the ratio test. All right, so if we write down the limit that's involved in the ratio test, it's the one that looks like limit as n goes to infinity of the absolute value of an plus 1 over an. And remember that an is just our name for the nth term in our series. Okay, so to get started on this calculation, we're going to write down an plus 1, which just means taking our formula for an and substituting n plus 1 in everywhere that we see an n. Okay, so there's an plus 1. And then we're going to multiply, we're going to divide by an, which is equivalent to multiplying by its reciprocal. So we'll take the an and flip it over. That's going to give us 2 to the n times 3 to the n over x to the n. Okay, so there's our first step. All right, now what we're always hoping when we do the ratio test is that we're going to get some cancellation here. And I notice one thing immediately, that those 2's are going to go away. And other things that you might notice is that we've got a 3 to the n over a 3 to the n plus 1. Okay, so those are going to cancel and put a 3 down in the bottom. And then we've also got an x to the n plus 1 over an x to the n. If we cancel those, we're going to get an x in the top. Okay, so let's rewrite what's left over here. What do we have? Well, notice that there's an x and a 3. Okay, those two things don't involve n's at all. And so since this limit that we have out front, it just involves n's, we're free to take the x and the 3 and move it outside. We have to remember, though, that there's an absolute value around all of this. So when we move the x outside, it's going to have an absolute value around it. Okay, so we're going to get the absolute value of x over 3 times the limit of the stuff that was left over, okay, the stuff that does have n's. Okay, and n over n plus 1, that's kind of all that's left. Notice that that limit has the form infinity over infinity, so we can use L'Hopital's rule on that. And we're just going to get 1. So the result of this calculation is x over 3, and remember that that x over 3 is the thing that we're calling r when we use the ratio test. Okay, kind of interesting because the r has a variable in it. Okay, so let's think back for a minute to what the r means in the ratio test. So you look back at the statement of the ratio test, it tells us that our series converges if r is less than 1. We're interested in figuring out where our series converges, okay? So we can think of it this way then. We need that value of r to be less than 1 for our series to converge. So it's going to converge if that r that we just calculated is less than 1. Okay, so that's an inequality that we can solve for x to see where our series actually converges. Right? So if we do some algebra here, multiply both sides of that inequality by 3, remember that the absolute value of x less than 3, we can rewrite that as kind of a 3-sided inequality like this. And that gives us an interval of x values for which we know that this series converges. Okay, I'm also going to draw a little picture, a number line. Okay, just so we can kind of picture this interval. So what we know so far is that we've got convergence between -3 and 3. Okay, well, what's left to do here? Well, you might remember that we have to test the endpoints, okay? Because at 3 and -3, if you were to take those and substitute those into absolute value of x over 3, you would get 1 for r. And r equals 1 is inconclusive, and so this ratio test that we just did will not help us determine whether we converge at the endpoints. We need to check the endpoints separately. Okay, so that's going to be the last part of our problem here, to check the endpoints. Okay, I'm just going to scroll down, give us a little bit more room here. Let's start with the left-hand endpoint, x equals -3. Okay, so if we take that and substitute it into the formula for our series, okay, here I think I'd like to scroll up and just take a peek at what the series looked like at the very beginning. Okay, so our series had the form that looked like this, way up at the top of the page. So we're really just taking -3 and substituting it into that formula for x. All right, so I'm going to do that. In the top, we're going to get x to the n becomes -3 to the n. Then the denominator is still 2 to the n times 3 to the n. We're just trying to decide, is that a convergent series or not? Okay, well, let's see. Let's do some algebra here. So -3 to the n we can break up as -1 to the n times 3 to the n. You might remember that little technique from problems in section 8.6. Denominator is still 2 to the n, 2n times 3 to the n. Okay, notice that the 3 to the n's cancel, and what we are left with, if we pull the 1/2 out, is 1/2 times the sum from 1 to infinity of -1 to the n over n. Is that a convergent series? Notice that it's an alternating series, and you might recognize it as a series that you already tested for convergence back when you studied this. Okay, we can confirm that just by direct calculation down here. Converges by the alternating series test because of two things. First, the limit as n goes to infinity of the bn, which in this case would be 1 over n, is 0. And bn plus 1 is less than or equal to 1 over n. Okay, so we're not going to write an entire proof, okay, but those are the two pieces that would tell you that this series converges. All right, and so what we've managed to figure out then is that we can add 1 point to this picture. We can color in -3 because we got convergence there. We checked the alternating series test and it worked. All right, so we've got one more endpoint to check. Okay, and that would be the right-hand endpoint. So if we take x equals 3 and plug it into our series, the x to the n in the top is going to be 3 to the n. Okay, down in the bottom we're going to get 2 to the n times 3 to the n. Okay, do some cancellation again. This time what we wind up with is 1 over 2 to the n, and if we take the 1/2 out, we've got 1/2 times the sum from 1 to infinity of 1 over n. And do you recognize what kind of a series that is that we're looking at? That's a p-series with p equals 1, and it diverges. Okay, because p is less than or equal to 1. All right, so we get divergence at the right-hand endpoint, which means that we're not going to color in the dot at 3. We don't have convergence there. And we're now in a position where we can state our answer. Okay, so what is the interval of convergence here? Well, our picture tells us that it's all x values between -3 and 3, including -3, but not including 3. We got divergence at that right-hand endpoint. Okay, and there's our answer.